Hello, Ikra. My name is Jansen Lee, and I work as a graduate student in Vanderbilt's Center for Rehabilitation Engineering and Assistive Technology in Nashville, Tennessee, United States of America. My talk for today is officially titled Swing Assist for Enhancing Stair Ambulation in a Primarily Passive Knee Prosthesis. However, I want you to think of this as a discussion on how a low-powered prosthesis can help make high-powered tasks possible. A system which cannot be controlled through an arbitrary trajectory in space is classified as an under-actuated system. A passive knee prosthesis can be modeled in two dimensions as shown here. When the ankle remains grounded, the system is fully actuated. Thus, it is mechanically possible for the user to dictate an arbitrary knee angle with their hip torque. However, if the foot comes ungrounded, the system becomes under-actuated. And while the user can still affect the knee angle through the double pendulum dynamics, they are no longer physically capable of dictating an arbitrary knee joint trajectory with an input torque at the hip. However, the vast majority of persons with transfemoral amputation rely on these under-actuated passive prosthetics every day to perform their tasks. And the reason why this is possible is the subject of a 1980 Tom McMahon paper titled Ballistic Walking. This paper concludes that in healthy walking gait, healthy knee flexion and extension is handled largely by the inertial link to the hip. And this explains how people who use passive prosthetic knees get around so well. For tasks like walking at normal speeds and the swing phase of stair descent, the person can achieve healthy knee trajectory inertially by providing healthy hip trajectory. However, many daily tasks, such as slow walking, recovering from perturbations, and stair ascent, require non-ballistic movements. For these tasks, achieving healthy or even adequate knee trajectory is not possible inertially with healthy hip trajectory. And it is in these situations that a prosthesis which is fully actuated is incredibly useful. However, historically, most devices which have been made to do this come with added cost, size, weight, noise, and notably high output impedance. Powered prostheses such as the Vanderbilt Power Knee are capable of providing huge amounts of torque to actuate the knee. This is done using a large motor with a large transmission. When a transmission is added to a system, the terms proportional to velocity or acceleration go with the transmission ratio squared. This means that for this device, the motor's inertia and viscous damping are effectively multiplied by 31,000. This causes impedance to motion to become very large and the device becomes difficult to backdrive from the output, and thus you lose the ability to passively perform ballistic tasks. Obviously, these devices can add power to the system to make up for this. However, making them respond as smoothly as an inertial system is a difficult control problem. Additionally, the increased impedance can make it more difficult to sense nuances in the person's actions, which can make it feel to the user like they are left to adapt to what the knee is doing instead of the other way around. Traits such as active torque output and impedance are often thought of as Boolean values. However, the reality is that these traits exist on a spectrum. When designing our knee prosthesis, our goal was simple: maintain the effective power dissipation and inertial coupling users love in passive prostheses, provide the capability to add just enough torque input to make the system fully actuatable during the swing phase of gait, and minimize the costs associated with adding this actuation. And this brings us to the device we have designed. We call it the Stance Controlled Swing Assist, or SCSA knee. This device uses a small, low-power motor in parallel with a hydraulic damper. The hydraulic system includes a one-way check valve, which means that the device is always free in extension. This actuator is then used in a slider crank configuration, along with a sensor suite and embedded system to make a fully functional knee prosthesis. And while I would love to talk more about the mechanical design of this system, this, along with level walking and perturbation recovery, was covered in depth in a previous publication. Importantly, the resulting device is our attempt to balance power and impedance in a fundamentally different approach to knee prostheses. Using a smaller motor and transmission, we maintain the low output impedance required for more nuanced intent sensing and passive ballistic movements. However, even our decreased torque output is more than enough to allow this device to control to and hold angles when the device is not loaded with the person's weight. Thus, we restore full actuation ability to the device during swing phase without sacrificing the ability to inertially link the shank and the thigh. The finite state machine used for stair climbing in this study can be thought of in three distinct phases. When the device is loaded, it remains in stance phase. Here, the hydraulic system is locked from flexing. Once the device is unloaded and the gating conditions met, the knee transitions into the flexion phase of swing. Here, the damping valve is open and the motor is used to control the shank's angle to maintain a 40-degree offset from the angle it made with gravity at toe off. Once the user's thigh velocity drops below a threshold, the device then transitions into swing extension, moving through a sinusoidal trajectory to the proper extension angle. At the same time, the damping valve is closed so that the device cannot flex when loaded. Once either the leg reaches full extension or it is loaded, the device transitions to stance phase. Again, the device is locked so that it does not buckle, but due to the check valve, it is free for the user to extend as they use their hip torque to move up to the next step. The finite state machine used for going downstairs had two states. The first was a damp stance, during which the active power addition was disabled and the hydraulic damping valve was set to a moderate to high damping in the flexion direction. Once the user unloaded the leg, assuming the gating conditions of knee flexion had been met, the controller would transition to the swing state. Here, the hydraulic valve was initially opened and the actuator was set to control to a trajectory in which the knee would initially flex a few degrees before extending smoothly. Once the maximum flexion angle at the knee was achieved, the valve would rotate back to a high flexion damping state to be ready for heel strike and the subsequent stance. To validate our controller, we performed a single subject stair ambulation test. Our participant was a 61-year-old male measuring 1.85 meters and at the time of testing weighing 98.4 kilograms. At the time of testing, he used a Rio knee for his daily use prosthesis. For our trials, the participant wore 7 Ascent IMU motion capture units, one on his pelvis, each thigh, shank, and foot. He was then asked to climb 2 floors of stairs totaling 52 steps at a self-selected pace, given a self-selected rest period, and then asked to descend down the same stairs. This process was repeated 2 times for both step 2 and step over ambulation. This was done first with his daily use device and then performed on our knee. In all cases, the subject was allowed to use handrails to better reflect how he would perform these tasks in his daily life. Because modulated damper knees allow users to descend stairs easily without power addition, our primary goal for stair descent was to show that our device was capable of providing the same smooth dissipation as these devices. For both step 2 and step over stair descent, our device performed similarly to the participant's Rio knee. I'm only showing the step over data here, as the task of step 2 stair descent requires virtually no movement at the knee. For all plots shown, the daily use data is shown in gray, our device in red, and when available, the dashed line is healthy gait data. The broader, semi-transparent regions indicate the standard deviation for the datasets. As you can see from the top plot, the knee flexes much more linearly over time with our knee as compared to the Rio knee. The damping values were tuned to user preference, and this could be tuned to match the damping profile of the Rio knee. The addition of power is visible in the swing phase of gait, as our device injects a small amount of torque to make sure the leg reaches full extension quickly. This is not necessary, but our participant preferred it. As expected, stair ascent is where we saw the most notable difference between the daily use device and our knee. As can be seen from the plot of the participant's knee angle, during the step 2 stair ascent, the passive daily use device gets virtually no flexion. This then causes issues we see on the next 2 plots. We see that the participant's affected hip moves forward very little and never clears 10 degrees of flexion. Finally, we see that the participant is forced to circumduct his hip much more on his daily use device when compared to our knee. Perhaps more telling than these plots, however, is a side-by-side excerpt from the video we submitted with our paper. Rewinding each to the point where the participant clears the stair, we see a visible difference in flexion at the knee. During step over stair ascent, we see a similar but even more stark difference than we did in step 2. Looking at our participant's knee angle, we see that with our device, his knee comes much closer to tracking a healthy trajectory, whereas with his daily use device, he achieves virtually no flexion. Again, we see that the participant is able to extend his hip much further in front of his body with our device, better tracking healthy trajectory. Finally, we see a decrease in the circumduction with our knee, as well as a narrowing of the standard deviation. This is visibly evident in the excerpts from the included video. Anecdotally, our participant noted that with his daily use device, he's often incapable of traversing upstairs in a step-over fashion, as the circumduction required makes his gait too wide for many staircases. In conclusion, with our device and control methodology, we were able to restore direct actuation to the knee during the swing phase while maintaining the ability to inertially perform ballistic tasks. We matched stair descent performance from a modulated damper knee and decreased the compensatory behaviors during stair climbing. Overall, our device enabled our participant to achieve joint trajectories more indicative of healthy gait during stair climbing. While the results of this work are promising, we know that this study needs to be expanded beyond a single subject. Additionally, we recognize that the ability of powered knee prostheses to add large torques could be impactful to the stance phase of stair ambulation. For this reason, we are collecting data to analyze stair ambulation ability and user comfort for a damped knee, a fully powered knee, and our device. Finally, we have developed a set of stairs with force instrumented handrails so that we can analyze the direction and magnitude of force a person is exerting with their arms. We hope this will provide us some insight in the previously mentioned trials as to whether the person is using handrails for left-right balance, vertical stabilization, or to offload the amount of work they would otherwise have to perform with their hip. Finally, I would like to close by thanking the National Science Foundation and the National Institute of Health, whose funding has enabled this research. I would additionally like to thank all the members of the Create Lab group, without whom this research would be much more difficult and much less fun. And to everyone who's listened to this talk, thank you for your time, stay safe, and stay healthy.